Hi everyone, I'm Subhasree Patro, and today I will be talking about a framework of quantum strong exponential time hypothesis. This is a joint work with Professor Harry Bowman and Dr. Florian Spielman. Okay, let's begin. Okay, let's consider the satisfiability problem. So, what is the satisfiability problem? We have a Boolean formula on n input variables, and we want to know if there exists an assignment to these variables that satisfies this formula. Let me give you an example. Say this is a formula on 3 variables, and if we set the variables values to say 0, 0, and 1, the formula is clearly not satisfied. But if I change the x3 value to 0, now the formula becomes satisfied. Now, if the formula is in this conjunctive normal form, that is, the clauses are connected by this and the variables inside the clause are connected by or, then we call this as a CNF SAT problem. Now, what do we know about CNF SAT problem? We know that it's an NP complete problem. So a polynomial time algorithm, and I mean here a classical algorithm, is highly unlikely for this problem. What else do we know? We know that when the clause length is not bounded, the best known classical algorithm takes 2 part n time. And the best known lower bound for this problem is n. So there's a huge gap between the known lower bound and the known upper bound. So like to understand this gap better, in 2001, Impagliazzo, Zane, and Paturi conjectured that there might not be any faster than 2 power n classical algorithm to solve CNF SAT on n variables. And they called it as the strong exponential time hypothesis, which, when abbreviated, is called SETH. Now, SETH turned out to be very useful in proving many lower bounds for many problems in sorry it for many problems in our complexity class NP. And not only that, it was also useful in proving lower bounds for many problems outside the complexity class NP. For example, it was shown that conditioned on SETH, strong simulation of various quantum computation models take exponential time. And here I mean classically. Now, surprisingly, SETH was also useful to prove lower bounds for problems in P. Now, the reason it is surprising because SETH talks about a exponential time problem, and it was useful in proving lower bounds for polynomial type problems. So that was a really interesting observation. And for example, the n square lower bound for proofs of useful work also was based on the um, belief that SETH is true. Now, for the purpose of this talk, we are going to only look at the polynomial lower bound for problems in complexity class P. Okay. Now, the first lower bound of that kind was given by Ryan Williams in 2005. So what he did is he reduced the CNF SAT problem to another problem called orthogonal vectors problem. Okay. Now let me just quickly define what an orthogonal vector problem is. So orthogonal vector problem is really easy to understand. It is you're given two sets A and B of n vectors each over like vectors of d dimension. And all we want to know is whether there exists elements in set A and another element in set B such that their inner product is 0. Okay. Now, clearly, there's an order n square algorithm for this problem, right? Because you can just check for every combination of AB, and then you can check whether their inner product is 0. Now, what was surprising is that, okay, I'll come there, and this reduction was really simple and elegant. Let me just quickly go through the reduction once. Now, remember, we are reducing CNF SAT to orthogonal vectors problem. Okay. So we are taking an input of CNF SAT, say it was phi, which had m clauses, and we are going to make an input to orthogonal vectors. Okay, so what do we do? Now let this x1, x2, and xn by 2, like the first half, with this be the first half of the inputs to the CNF formula. And let x, can you see my cursor, by the way?
Yes.
Okay, cool. So, and let this xn by 2 plus 1, xn by 2 plus 2, and so on till xn be the second half of the inputs to this 5. Okay. Now, for every possible partial assignment, we create two lists A and B as follows. Okay. So, now look at this figure here. We are going to create two lists for every particular assignment of partial assignment of these variables. How do we do that? Now, the number of rows in this table is going to be 2 power n by 2, because that's the number of possible partial assignments that we can have. And the number of columns to this table is going to be um, m, because we are going to we are going to match the elements, the clauses to this. Okay, and what we are going to do now, suppose we want to fill in the first cell of the first cell here, which is the element of first row and first column. Okay, now what we check is, if this, if under this partial assignment my clause c1 evaluates to 1, then I put a 0 here. And if I can't determine what happens with this assignment, or say it evaluates to 0, then I put a 1. Okay, and I fill in the clauses, I fill in the cells uh, for every other clause here, and I fill in the cells again for every other possible assignments here, and I do the same thing for this other list. Okay, now if I run my orthogonal vectors problem on this set of inputs, what I will find is, if there is a element that has inner product, if there is an element here that has inner product with an element here as 0, then that assignment in total becomes the satisfying assignment for the CNF formula. Okay, thus proving that um, if I have a faster than n square algorithm for orthogonal vectors, my CNF SAT would also have a faster than 2 power n algorithm, which would make SETH false. So hence the lower bound of orthogonal vectors problem as n square. Okay. Now, another interesting thing that happened was, this orthogonal vectors problem became very useful in proving lower bounds for other string comparison problems. For example, edit distance, freshest distance, LCS, and all. And that reduction was also really interesting. What they did there was, by the way, this reduction was first given by Bakkerson and Dyke, and then it was generalized by Brinkman and Kuhlmann. Now, what they do there is, now remember, orthogonal vectors had two lists, right? It had A and it had a list B. Now we create two long strings, which is XA and XB, corresponding to these sets. Now, what these strings contain is actually something called gadgets, which only depend on the values of the vectors in these lists. Okay. Now, this whole thing, the gadgets and the strings are constructed in such a way that edit distance or freshest distance or LCS between these two long strings, like the value, indicates whether an orthogonal pair exists or not. Okay. Now, the interesting part in these reductions were that it gave us the n square lower bound for string comparison problems, and it gave an n square lower bound for orthogonal vector problems, which in the classical setting were actually tight. So this was very useful, because this was an explanation why we were not able to find any better than n square algorithm for orthogonal vector, or better than n square algorithm for edit distance or LCS and all. Okay, but all this is in classical setting. Okay, now what is interesting is, set doesn't like it doesn't hold in the quantum setting. The reason it doesn't hold in the quantum setting is as follows. Now, um, yeah, what one can do is, one can run the Grover search subroutine over all the possible assignments, and the number of possible assignments is 2 power n, right? So if I use a Grover subroutine on over all these possible assignments and to check if anything is satisfied or not, I can do that in 2 power n by 2 time, because I'll be only querying 2 power n by 2 of these assignments. Okay, so clearly that renders SETH false. Now, because of this, we now see that the set based lower bounds will not directly hold in the quantum setting anymore. Let's just review the oh sorry and so it is natural to conjecture that maybe there's no faster than 2 power n by 2 quantum algorithm to solve CNF SAT on n variables. Okay, while we conjectured this in our paper in 2019, Aronson et al. Also at almost during the same time conjectured this in their paper. Okay, but let's see how useful is this basic Q set. Okay, we are, by the way, we call this as Q set. We just add Q to it. Now let's review the same problems that we had discussed earlier. So we had this reduction from CNF SAT to orthogonal vectors, and from orthogonal vectors to string comparison problems. And there in the classical setting, it was really nice because it was the bounds were tight. Okay, but now what do we have in the quantum setting? Now in the quantum setting, our basic Q set says that CNF SAT requires 2 power n by 2 quantum time. Okay, now using the similar reduction, we can show that orthogonal vectors requires uh, like linear amount of time. Okay, and then again using the similar to classical reduction, we are able to show that the string comparison problems will also require linear amount of time. Okay, but while this is interesting in the case of orthogonal vectors problem, because we have a linear time algorithm to check whether there exists orthogonal vectors or not, which is very simple, right? Because you're now going to Groverize over all these tuples that you can have between A and B. And there are n square pairs. So now you Grover over them. So you kind of have a order n time algorithm, quantum algorithm. So this is tight. But in the string comparison problem, we do not have anything better than the classical algorithm in the exact edit distance or fresh distance or LCS case. And the lower bound known is linear. So there's a quadratic gap that we are not able to explain because of this basic Q set. Okay. So that kind of motivated us to introduce the Q set framework. So now I'm going to recall the CNF SAT problem again, because you'll soon understand why I'm revisiting this. Now, what is the CNF SAT problem? We are given a CNF formula with n input variables. Okay. Now we want to know if there is an assignment that satisfies this formula. So in another sense, if I see, what we are trying to do is we are trying to see the OR property on the truth table of this formula. And what do I mean by truth table of a formula? The truth table of a formula of n variables is a 2 power n bit string, which is concatenation the uh, of the result that the formula evaluates to for every possible assignment. So if you just look at it, it's like what is the output of phi on all zero input concatenated with what is the output of phi on say 0001 and so on up to all these possible assignments. Okay, so that is a 2 power n bit long string. So I could like kind of rewrite CNF SAT on phi as computing a property, say OR, on this truth table of phi. Okay. Now we know the best known quantum algorithm for CNF SAT takes order 2 power n by 2 time, because we could Grover over all possible assignments, right? Okay. Now we know the quantum query complexity of this OR property on 2 power n bit string is also 2 power n by 2. Okay, I will explain why we are discussing this. Okay, but what if we are not we are interested in some other property of satisfying assignment, meaning given a CNF formula with n input variables, What if we are interested in knowing whether there are an odd number of satisfying assignments to phi, or even number of satisfying assignments to phi, or say count of the number of assignments satisfying assignments to phi, or some property like that. Okay. So instead of defining CNF SAT, now I define a variant, which is say parity CNF SAT, which is nothing but parity CNF SAT on a formula phi is nothing but the parity property on the truth table of phi. Okay. Now, how much time does it take quantumly to solve parity CNF SAT? Let's see. It is and we know that the quantum query complexity of this property of parity property on all 2 power n bit strings is actually order 2 power n. Okay. Now it appears like on the side of it, it appears as if we cannot have a Grover like speedup for CNF parity CNF SAT. Okay. So we would like to conjecture that there is no faster than 2 power n quantum algorithm for solving parity CNF SAT on n variables, which is analogous to parity SETH, which also has been defined decades ago. Now, till now, whatever we have discussed, it feels like um, these conjectures of like computing CNF SAT or computing parity CNF SAT on formulas is like query complexity of those properties on its truth tables. Okay, but I will now show you. But what happens is something actually. These conjectures indicate something much stronger. Okay. Now, recall that whenever we talk about CNF SAT problem, we are talking about the formulas which are of polynomial size formulas, right? Because otherwise, it doesn't make any sense to consider them as NP complete, like NP problems. Okay. Now let's take the set of polynomial sized CNF formulas. Okay. Now we have some of them. Okay. Now consider the truth tables of these poly-size CNF formulas. Okay. Now the number of the size of this set would be 2 power poly n, right? Which is really small compared to the size of the the size of the set of all these 2 power n bit strings, because that would be 2 power n. Okay. Now if I want to look at, say, the query complexity of some property or of property or on all these 2 power n bit strings, then I know that the query complexity is 2 power n by 2. Now, query complexity for this property or on the small set, this is like the small set of 2 power n by 2, 2 power n bit strings, is also actually 2 power n by 2. That is because the adversarial set that is used to prove this query complexity for this property or actually can come from these small CNF formulas. Okay. But when we talk about parity, the query complexity of parity of 2 power n bit string is 2 power n when we look at all these strings. Okay. When our adversarial set is this big. But when you make this set small, then parity, the query complexity of parity on this small set is actually quadratically lower. It is 2 power n by 2. Now, this is a very important result because this holds for any property actually, and it's not only for parity. Now, we will be looking at this algorithm in a short while, but this is a surprising fact. Okay. So now, while this algorithm is very nice when it look when it when we just look at the query complexity, but when we see the time complexity, it is horrible. So that motivated us to define something called compression oblivious properties. So what we said is, we say a property is a property P is compression oblivious if the quantum time taken to compute this property on set of truth tables of small formulas, which is like the time taken to compute uh, this property P on this small size. Okay. But mind you, we're talking about the time taken, okay, not the query complexity. On the small formulas is lower bounded by query complexity of all strings. Okay. So clearly from the example that I gave you before, OR is compression oblivious. Now our parity Q set that we had defined earlier will imply that parity is also compression oblivious, because we noticed that the time take, like if parity Q set is true, then time taken to compute parity on this small string will still be very high. So we could show that it is parity compression oblivious. So it is reasonable for us right now to believe that parity is a compression oblivious property. Okay, that is because we believe that parity Q set takes 2 power n time. Now we define this Q set conjecture. What we say is, given a formula phi, for all compression oblivious properties P, the quantum time taken to compute the property on the truth table of that formula is at least the query complexity of P on all 2 power n bit strings. Okay. So now how is this different from the compression obliviousness? So when we are given a formula, we are given the description of formula. Okay. And the description could be very small because it could be poly of n. But for compression oblivious property, we are given the truth tables. Okay, which means the string is very big, but the number of strings that we could have is less. So that is the difference here. Okay, and we kind of see that our general QSET implies basic QSET, and if we take our QSET and we assume parity is compression oblivious, that implies parity QSET. You don't have to worry about this part. Let's move on. So now, but okay, why do we define all this? So we the motivation for defining all this came from actually the proof for n power 1.5 lower bound for edit distance problem. Now, remember, I talked about the string comparison problems before, and I told you that in the quantum setting, the best known algorithms in the quantum setting is actually the best known algorithms in the classical setting. But the lower bound known was just linear, that is n. So there was a big gap between that. Okay. Now, using our framework, we are able to bridge the gap a bit further, and we are able to show that under our believing that our Q set is true, edit distance or longest common subsequence, this kind of problem requires n power 1.5 quantum time to solve. Okay, so let's just review this edit distance problem once to get an idea. So say we have two strings A and B, and it is defined over some alphabet set sigma. Then we define edit distance between A and B as the minimum number of operations required to convert A to B. So let's say, for example, we take beagle and patches. Now, by the way, the operations could be insertions, deletions, or substitutions. So here the edit distance is 4 because one of the best ways is to delete this E to and to insert a D, and to delete this L and insert a S. Okay. So the way we approach, the way we are able to get the reduction work is we actually study the classical reduction from satisfiability to edit distance problem given by Abod and all. And we slightly modify the reduction. And then we notice that this reduction actually computes not just satisfiability, but it computes some other property on these CNF formulas. And the property turns out to be something very similar to this OR and OR of majority property. Now, what is OR and OR of majority property? So suppose you have a n bit long string, and that is divided into root n blocks of root n bits each. Okay. Now, if the question asked is there a block of string which has majority of ones in it. Okay, then that is the OR of majority property. Now, for this property, the query complexity turns out to be n power 0.75. This is a, oh, I forgot who, okay, this was an interesting result. Okay, you could use this adversity method by Ambani's to get this result, but there was another cool paper, now I've forgotten the name, also which you can use directly to plug in the values here and plug in the values here, and then get this n power 0.75. Okay, and but remember that p edit is not exactly OR of majority; it's very close to that. But in our paper, we were able to show that this query complexity of p edit is also n power 0.75 on n bit strings. Okay, and we use the quantum adversary method by Ambani's. Now, assuming p edit is compression oblivious and assuming that QSETH is true, we are able to show that when we are given a Boolean formula, the time taken to compute p edit on the truth table of this formula quantumly requires 2 power 0.75 n, and which, because of the reduction, translates to n power 1.5 lower bound for this edit distance problem. And similar result is there for this longest common subsequence problem as well. Okay. Now, this must be a concerning fact for you guys that and girls, that we are assuming p edit is compression oblivious. Okay, but just bear with me here. I'm going to revisit this assumption soon. Now, another application of QSET that we noticed was that if we assume parity is compression oblivious, which is very believable, we are able to show that this proofs of useful work scheme holds in the quantum setting as well. And here also, we are again talking about assumption that parity is compression oblivious. Now, the reason we assume that these properties are compression oblivious is because it is not easy to prove a property is compression oblivious. And it's not because, okay, there's a reason why it's not easy. We are in fact able to show that for many properties, proving P is compression oblivious would actually separate P from P space. So if we indeed prove that some property of this kind is compression oblivious, I would be getting a lot of money for sure. So, okay, now we're going to prove this theorem that if parity is compression oblivious, then P is separate from P space. Okay, so we prove this by contradiction. So we show that if P is actually indeed equal to P space, then parity cannot be compression oblivious. Okay, so let's recall the definition of compression oblivious property again. Oblivious property are those properties P where quantum time taken to compute them on a set of truth tables of small formulas. So it's a small set of big strings, but it's a small set. It is not spanning the entire set of capital N bit strings. Okay, is at least query complexity of P on all strings. Okay. Now, remember that the query complexity of parity on all strings is of length n is order n. Okay, which is equivalent in the classical setting as well. So for parity to be compression oblivious, we need that the time taken to compute parity on this small set of n-bit string is at least n. Okay, but we will show that if we assume p equals to p space, we can actually compute parity in such a setting in significantly less time, that is root n times poly n, order root n times poly n time. Okay, so and to prove this, we actually use we use a algorithm of another problem, and so I'm going to take a small detour there, and then we will come back here. Okay. Now, so the algorithm that we used is for the problem Oracle named as Oracle identification problem. Okay. Now, what is this problem? We are given a set S of strings of length n. Okay. Now, this set doesn't have to contain all possible n-bit strings. It can be like just a subset of these all possible n-bit strings. Okay. Now, addition to that, we are also given query access to another string, which is also of n bit. Okay. Now we want to find this string x using the least number of queries to x. Now, clearly, if we are allowed to query n, like if we are allowed n queries, I can just query x n times and get this entire string. But clearly, I want something much better than that. Okay. Now, I'm going to show you a quantum algorithm which can achieve this requirement in order root n times log s number of quantum queries. This algorithm was given, and this is a simplified algorithm of many complicated ones that they further give. But this was introduced by Ambani's et al. And Robin Kothari long ago. Yeah. Okay. Now let's see this algorithm. So now what we need to do here is we maintain something called a majority string, which is also of n bit, but the majority string is simple. The ith bit of majority string is set to 1 if majority of my strings in S had 1 in its ith bit. Okay, is this clear to everyone? Okay, I'll just continue. Otherwise, it's set to 0. Okay. Now, once you have this majority string, which is kind of based on this entire set S, I can, using Grover's subroutine, check if there's a disagreement between this string M and this string X that is my that I have Oracle access to. And to check, like to get in a disagreement, I need root n number of queries, order root n number of queries. Okay. Now, if there is no disagreement, then clearly my x is equal to m. So I have found this x with just root n number of queries. But if there is a disagreement, then say the disagreement was an index j that the Grover's subroutine returned to me. Okay. Now I know that my x is not the value, like at my xj, my the value of xj is not the value of mj, right? That means all those strings that had mj equals to not equal to x can be removed from the set because they will not be the elements that will match with x. Okay. Now, because this was a majority string, what I have done in this process is I have taken at least half of these elements in S out. Now I repeat the same process again. Now I create a new majority string, but on the smaller set S. And I repeat this process. And I keep doing it till I find a disagreement, till I don't find a disagreement, or till my set becomes 1. So the number of times I am repeating this process is going to be log of the size of S. And because because for checking the disagreement with every M, I need root n queries. I just multiply. So this is the algorithm, which is much lesser than like uh, asking X for every possible bit, right? So now we'll come back to we come back to our original question, that is we wanted to show that if parity is compression oblivious, then P will be separate from P space, and we were trying to show it by contradiction. So we were going to assume P equals to P space, and with that assumption we are going to show that parity cannot be compression oblivious. Okay. Now I'm not going to go with the definition of compression oblivious again, but just a reminder, query complexity of parity on all strings is order n. And so if we want parity to be compression oblivious, we want that parity on the small set of truth tables should also take at least n. But with this assumption of P equals to P space, we will be able to compute parity in almost root n amount of time, quantum time. Okay. So here also we are going to check the setup again once. Okay. So what is the setup here? We have this set S, which is, say, set of all polycized formulas. Okay. Now I can kind of imagine a set S which is of polycized formula, because I can just uh, fix a poly length, and then I can go over all these uh, possible descriptions in that formula. Okay. Now, say I'm told that there is a circuit, like we have access to, we have black box access to a circuit C, which is a set which belongs to this big set. Okay. But we only have black box access. What do you mean by we have black box access? We don't have the description of the circuit, but we have access to the truth table of the circuit. So I can always ask, oh, what is the value of C when computed and, say, on all zero string? Or what is the value of value when C is computed on, say, all one string? So these kind of information we have access to, but I cannot ask the description of C. Okay. Now, but by chance, if someone actually gave me this description of C, someone told me, okay, here is a small circuit and here is the whole description of the circuit, then under this P equals to P space assumption, I can compute parity of the C in poly n time, right? And that is, we can do that because now remember, this P equal to P space assumption is a very big assumption. So what we could do is we could load this description of the circuit on our workspace in the Turing machine, and then we can run this circuit on every possible assignment, right? But when I'm running this circuit on every possible assignment, I can continuously reuse the space, which means under this P equal to P space assumption, I'm kind of reusing my time as well. So I will only require poly an amount of space, which under this assumption translates to poly an amount of time. Okay. So, so if I can get this description of C, then I'm done. Okay. So now what I'll show is, excuse me, the simplified Oracle identification algorithm that we discussed can be used to extract this compressed form of C in almost order root and time. So we again do the same thing. So what we are trying to do is we are going to run a Grover subroutine over this truth table of C and this majority string MK. Now, why am I saying it is MK instead of M? Because we are going to do this at every, like at log s different stages, right? So, but unlike the earlier case where we were not worried about the amount of time it was taking, we had enough resources to write this entire M string again and again. Okay, but now we don't have that much time. We want to efficiently compute these bits under this P equals to P space assumption. Okay. So now when a Grover subroutine queries, it is going to ask for some, like it's going to query over root and number of indices, but at any point it is going to ask what is the value of, say, xi, and what is the value of this mi at the stage k for any k. Okay. Now I'll show you that under P equals to P space assumption, I can compute this mi at any stage k in poly n amount of time. Okay. So what do we do? So in this case, we now maintain a list of disagreements. Now, what is the list of disagreements? Now, see, if we are at the kth stage of this algorithm, that means we have already found k minus 1 disagreements that were there between x and m, and where m was uh, like updated at every stage. Okay. But now, given that this number of disagreements is not going to be more than log s, this list is not going to be too large, and we have that much space in our uh, like we have that much time as well to compute this. Okay. Now, for every circuit D in my original set, okay, I can check if D disagrees with any element in this, by actually running D on all these indices, that is I1, and like by running D on I1 means by running D on binary representation of I1 and so on. Okay. Now because P equals to P space, when D runs on all these indices, I can continuously reuse the space. So I can kind of I'm reusing the time itself. Okay. So for every circuit, I can check in like I can check this in log s time poly and time. Okay. Now what do I have now? If the so if my di was disagreeing with any of this already existing list, then I can discard it. I know that that is not there in my set s at kth stage. Okay. But if it was agreeing, if it actually was matching to the value of xi here, then I know that it is present in my final, but then it has the potential to be present in the final set S. But how do I compute majority or parity there? Yeah, majority there. I can again check for all such Ds. I can keep a count and I can check whether uh, it evaluates to 1 or 0, right? So that way I can return this mi k in poly n amount of time. Okay. Now this entire process has taken root n times poly n amount of time. Okay. So now what we have done, we have found out the compression form of C using this simplified version of Oracle identification algorithm and the assumption that P equals to P space. Now, again, with this P equal to P space assumption, given that we have this compressed form, like I told you before, we can compute parity on this compressed form in poly n amount of time. So we have ended up computing parity in this setting in almost root n amount of quantum time, okay, which is much less than the query complexity of parity on all strings, hence contradiction. That's how we prove this theorem. Okay. So now future directions. So we believe this that this QSETH framework can be a potential tool to prove conditional low bounds for many other additional problems in BQP. And the low hanging fruits will be other string comparison problems. And additionally, we think this notion of compression oblivious properties are also very interesting. So it'll be nice to invest some time to understand what would happen if parity was not compression oblivious. So what we have now is, if parity is compression oblivious, we know that P is not equal to P space. But what if parity is not compression oblivious? Does that violate some complexity theory notions that we believe in? And another last direction, like another future direction, could be to understand reductions from other central problems. So right now what we did is we kind of assumed that CNF SAT, we conjecture that CNF SAT takes some amount of time, and then we are giving lower bound some of some other problems, and there we are basing hardness of those new problems on hardness of CNF SAT. And in the classical setting, there are there's a amazing survey article by Virginia Williams, where she also considers some other core problems like threesome and APSP. So this is a nice area to see in the quantum setting as well. Okay. So yeah, this is it, and now I'm ready to take questions. So thank you.
Mm. Thank you, Dee. So, are there any questions to Subhasree?
So one quick question:
Yeah, sure.
is there so you showed lower bounds for these problems in P, right? Is there kind of anything that you can say about, let's say, exponentially hard problems? Is problem in NP? I mean, can you prove new lower bounds using your framework, or basically you just use the QSETH, the 2 to the n over 2 conjecture that you stated in the beginning, and you just get the bounds from that.
No, it's it's not like we can't use, like we haven't tried it yet, but
Okay.
there's nothing in that that stops us from using it for other problems. So
I mean, in the sense that what I'm saying is that do you have any hope that there is any better lower bound that you can prove than what you would get with the basic conjecture, the 2 to the n over 2 conjecture?
so okay, I'll have to check in the NP, like in the NP setting, basically other exponential low bounds. I'm not
Yes.
sure of that. I haven't seen
Okay.
that.
Okay. I
But
mean, I was kind of surprised that you didn't even mention this in the future question. So that's
okay, okay.
so.
Maybe I need to update that. But for that, I have to first check what all has happened there and
Okay.
then update.
No, so
Thanks.
was there a good reason kind of to not mention this as well?
No, 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 no. I think
Okay.
it
Okay.
is. Yeah, it was just that we were focusing on these things first. So
I see.
actually, what
Okay.
happened is we first gave this result for edit distance,
Mhm.
and we soon realized that we could extend this for LCS. So
Yes.
now we think maybe other string comparison problems also might be might have better lower bounds under
Okay.
this. And but simultaneously we also started looking at the other core problems like threesome and APSP.
And
So
okay, so you mentioned about APSP and threesome. Can you
hmm.
just quickly say what is known about this in terms of lower bounds?
Yeah, so in threesome also, like it's believed that this threesome, do you know the threesome problem first of all?
Threesome, yeah. So basically, you have. Okay, I mean, I think there are variants. I mean, can you tell me
Yeah, yeah,
what
there
is
are
it?
variants, yes. So
So what is the
like
problem that you?
yeah, so all of them are pretty much equivalent actually in the variants.
Mhm.
So you can consider this problem like so you have this list S, and you want to know if there exist three elements in this list,
Yes.
such that like say A, B, and C,
So
where
that
A
A
plus
plus.
B equals to C.
Mhm.
Okay, now classically it is like the best algorithm known is takes order n square. Okay,
Yes.
now it's a simple but nice trick. Like definitely you can do it in n cube, but you can also do it in n square. So what you
Yes.
can do is imagine you sort this list. Okay,
Yes. Yes.
now you make two more copies of it, suppose.
Right.
So now you have three copies of the sorted list S.
Mm-hmm.
Now that took you n log n time, right?
Yes.
Okay, 3 n log n time or whatever. So now what you do is you take first two lists. Now you
Mhm.
check for every pair there.
Yes.
Okay. Now you with like very smartly you can now check for like using say binary search whether
Right.
this A plus B is equal to C,
Sure.
right? Now so this algorithm will take you n square times log n because the binary search takes log n.
Yes.
Okay, but there's another trick, very easy, but I won't be able to explain you like while talking, where you can even lose this log n factor as well.
Okay.
Okay, so now classically we have this cool n square algorithm,
Mm-hmm.
and people are not able to find anything like strictly subquadratic for threesome.
What? Okay. Even
And
quantum.
no, in quantum now you can actually do it in linear time, linear quantum time.
I see.
Like again I'm ignoring the log n factor there because you could
Okay.
use a similar trick. So you sort it, that takes n log n. Okay,
Yes.
and now what you do is again take these pairs and
Okay.
binary search over the third list.
Sure.
But now when you're searching over all these pairs you're going to use grover over that,
Sure.
so you lose this square root factor,
Sure.
not factor, like the
So,
square root power,
basically you'll have n log n essentially.
n log n, yeah. So now it is conjectured that classically there is no subquadratic algo for threesome, and quantumly it is conjectured that there is no sublinear algorithm for threesome.
Right. But
And
but
then,
but no one knows any lower bounds, right? Or are
oh
there
no, no,
any?
no, people have proved many lower bounds. So there's a lower bound by Petrascu, there's lower bound by Virginia Williams.
But
Like
not matching lower bounds. Are there matching lower bounds? No.
some of them are matching as well. Yeah,
Okay.
like tight lower bounds. I mean,
I
yeah.
see. Yes. Yes. Yes.
So yeah.
Okay.
So
And for APSP,
Now,
Again, like,
PPSP, I haven't, like, I had at one point read some of these lower bounds, but I haven't worked in the quantum setting yet.
okay, okay, thanks. Okay, thank you.
Okay. So are there any more further questions? Hi Dee. So I have one small question.
Sure, sure.
So is the QSET your is does it have any implications for, like, let's say, instead of NP complete problems, for like QMA complete problems, like local Hamiltonian or something like that?
No, I haven't, we haven't, okay, I haven't thought about it or checked.
Okay.
Maybe my prof
because
will have.
because I was expecting that, like how Seth was saying that exponential time for NP complete problem, QSET would probably be for some local Hamiltonian or something like that. So
No,
that was
that
my
will.
but
Uh,
but okay.
no, okay, I'm not even sure. Like, I don't see how yet. But yeah,
Okay.
definitely these are interesting directions for me to think about.
Mhm.
Mm, yeah, I'll have to think about it and actually read about these things more first.
Okay. Okay, maybe if not any other further questions, maybe we should thank Subhasree for our talk on QSET, and maybe we can stop the call here. Yeah, thank you, Dee. Uh, Thanks for your time.
You're welcome. Mhm.